Okay, let me continue today with lecture number 2. We are talking about continuous Fourier series. If you have a continuous periodic series function f of t, then we can say that that function, which have a period capital T, can be expressed as a constant a naught plus summation of ak cos k omega naught t plus bk sine k omega naught t as shown in equation 22. So any periodic function continuous can be expressed according to equation 22. That means we have to calculate the constant a naught, the constants ak, and the constant bk. Now, according to equation 23, that we can prove later on, we say that the constant a naught is given by the formula 1 over the period capital T times the integral of the given function f of t dt. And the next two constants, ak and bk, will be shown in the next slides. So for example, the constant ak in the Fourier series can be given according to this equation, which is shown in equation number 24. Now, one thing we have to be careful to find out, this constant ak turn out to be an even function. And the reason we say ak is an even function is because if we replace the index k with the index minus k, let's see what happens. If you replace the index k with the index minus k, that means this k here has to be replaced by minus k. And we know that cosine of k omega naught t is the same thing as cosine of minus k omega naught t. So because of that reason, we conclude that ak is the same thing as a minus k, and therefore the constant ak is an even function here. Similarly, the constant bk is given by this formula, which is shown in equation 25. And by carefully observe this equation 25, we can see that the function bk, the constant bk calculated according to equation 25 should be an odd function. Bk is an odd function. And the reason is because if you replace this constant k with minus k, then we know sine of k omega naught t is equal to the negative of sine of negative k omega naught t. So for that reason, b sub k is equal to the negative of b minus k. And that's why we say bk is an odd function. Okay, so in the previous slides and in this slide, we already give you the formula to calculate a naught, ak, and bk. Now let's try to understand where those formulas come from. So let's start the derivation by looking at the Fourier series again, shown in equation 26. Basically, Fourier series say any periodic function f of t can be expressed as a linear combination of a constant a naught plus summation of ak cos k omega naught t plus summation of bk sine k omega naught t. This is what we have on the previous slide. Now we want to do is just integrate both sides of this equation with respect to time. We integrate both sides of the equation with respect to time. Okay? And you can see clearly that based on the lecture number 1, we already proved at that time that the integral of cosine k omega naught t is equal to 0. So this integral here is equal to 0. And similarly, also from the lecture number 1, we also proved that the integral of sine of k omega naught t, that integral also is equal to 0. And therefore, all you have left from the equation 26 will become equation 27, which is shown right there. So on the left side, we have the integral of Lt dt, and that comes from equation 26. And on the right hand side, the integral of a constant a naught dt is just equal to a naught times t. And we have to evaluate between the lower bound 0, the upper bound is capital T. So on the right hand side, it will become a naught times t, and therefore we can solve for a naught, which is given according to equation 28. So I already proved to you why and how do you get the formula to calculate the constant a naught of the Fourier series in here. Well, the next thing we want to prove to you is how do you obtain the formula to calculate, let's say, the constant bk. Well, in order to prove that, let's look at equation 29. Let's look at equation 29. We start with the Fourier series again. It says any periodic function f of t can be expressed is equal to a constant a naught plus summation of ak cos k omega naught t plus summation of bk sine k omega naught t. That is what Fourier series is. So from that Fourier series equation, we want to multiply both sides of equation 29 by sine of m omega naught t. So multiply both sides by this quantity. So multiply both sides by that quantity, multiply both sides, each term with that quantity, and multiply both sides with this same quantity. And then after that, we integrate it. After that, we integrate it. Every term we want to integrate after that. We want to integrate it every term. Based on the lecture number 1 that we already talked earlier, we say the integral of sine m omega naught t should be equal to 0 based on the previous material. So this is 0. Similarly, the integral of cosine of k omega naught t is also equal to 0. The integral of that term is also equal to 0. Now let's look at the last integral. The last integral here, the integral of sine k omega naught t times m omega naught t is also equal to 0 when k is different from m. The only way that is not 0 is when k equal to m. So when k equal to m, this integral right here will become the integral of sine square, because when the index k equal to m, sine k omega naught t times sine m omega naught t becomes sine square k omega naught t. And from lecture number 1, we already proved to you that this integral of sine square here between 0 to the period capital T is equal to the period T over 2. We already proved that. So from equation 30, we should be able to calculate the constant bk. We should be able to calculate the constant bk. And that constant bk, based on equation 30, can be solved as here. And the reason is, I told you before, the integral of sine square term is equal to t over 2. So we already show you the derivation for the formula for the constant bk. And then a similar derivation we can use to figure out the formula for ak. And that should conclude this lecture number 2.